Previously. Well, previously as in like a few days ago.
Cool. Like in the textbook or elsewhere?
Various places.
Sure. All right. Subject is on mirrors and lenses. So this chapter is very much going to be talking about how, essentially, let's see. Well, I need to get those out, actually. Like if you ever look on a bus and you see that like crazy kind of like curved mirror that kind of shows you a different image, and then also for all of you guys that regularly do your makeup in the morning, if you have a makeup mirror, adjust some people, whichever, okay, that kind of magnifies and enhances and that type of thing. That would be mirrors. And then lenses are, of course, glasses lenses or lenses being used in telescopes and microscopes. Basically, the goal is by the end of this that you would be able to kind of construct a telescope. So here we go. What's the difference between a virtual image and a real image? Because it's the longest?
No. Because I read it, like, it kind of makes sense in the brain.
Okay. What you got? Answers? Hands?
Concur.
What you got? There we go. Longest. Okay. The image is created by a flat mirror alone is what? Virtual with magnification 1, real with magnification 1, virtual with magnification greater or less than 1, real with magnification greater or less than 1. Should be 1. A mirror creates an image of an object. It is upright. It appears to be slightly smaller than the object itself. What kind of mirror is it? Concave, convex, flat, or unknown? There's not enough information given.
Concave.
Switch go.
Wait, I'm thinking of one.
There's concave. Some more. The sun is setting at the bottom edge just as it touches the horizon. The sun is where it actually appears to be. The sun is below the horizon. The sun is about 1 diameter above the horizon, and the sun is 2.9 degrees above the horizon.
2.9 is so specific.
That's very specific.
I'm gonna go with 4.
But it doesn't have the
because of the specificity. So
Yeah.
we're not actually going with content anymore. It's 100% just like with just like
This
test
seems
taking,
the smartest.
strategies.
Yeah.
All right. Well, two was the answer. 4.
Okay. Which of the following do not suffer from chromatic aberration?
That's a lot of words.
I think
Been
it's,
talking about-
I disagree with
Is
you. It's about
convex-
10.
Does
There are
convex
problems with
bend
It's
towards,
also
or
a
does
white
that bend away?
background though, so it's like hard to read.
Convex be like this.
What is that?
Perspective?
What you got? The answer is mirrors. All right, here we go. So let's start talking about a flat mirror. So we're going to really push this chapter, something that I talked briefly about last chapter. And the main idea is this. Reflection, what actually happens, law of reflection is what we discussed last chapter. We're going to discuss a lot more is our perception of that particular reflection. And the main thing to understand is that our brain assumes that rays of light go straight. Okay? So what we can do then is we can look at a handful of rays of light. For example, you have an object in the top part, okay? And the object to the mirror is some distance p away. Now, the letters we use in that spot, I don't care. But I will also say that the AP equation sheet does not use P and Q. They use DO and DI, which is, as you would imagine, the distance to object and the distance to image. I don't care which one we use, but I would probably suggest that we all do the same one. The value of using P and Q is it's one less letter to write. Okay. The advantage of using DO and DI is it's a little bit more straightforward, especially early on which one's which, and also it's what the AP equation sheet uses. Which would you like? DO, DI. Any disagreement there? Okay, so whenever I do problems from this point forward, and all equations up here we will have to shift, I will be using then dO and dI. All right, so you have some object over here. So this could be anything, an apple, a person, or whatever. Okay, in this particular case, it's like looking above. So this would be, to kind of draw a perspective, imagine this is a mirror right here. And well, actually it is. I can actually see specularly right now. And I want to look at that guy right there. Okay, where does my, actually let's go with, let's bounce back and forth here. I'm going to look at the projector. Okay, so you can kind of see my setup right here. Okay, the projector is above me. Where do I see the projector? I see the projector over there. Yes? Now, obviously our brain then works out the fact that, you know, okay, so I see it over there. I know it's technically behind me from experience, but the idea is, where do you actually see it? The image is where you actually see the object. Okay? So, in this particular case, also notice something very important. In this picture, where I am has no bearing whatsoever. Where the eyeball actually is has no bearing on DO or DI. Yes? We see that? Meaning, when I look at the projector, what is DO? Like if I could walk DO, what is it? It's the distance I could measure from here, underneath, all the way to the screen here. And what is DI?
Same thing.
Not quite.
The distance from where you see it in the reflection to
Right.
where it's actually coming from.
Technically, it would be the distance from here through the door out into the hallway to where I technically see it in space, right? Now, is it actually there? No, it's not actually there. But that's where I see it. So what our eyeball does is watch my finger here. We'll trace this top ray. It sees one ray leave, which hits the top part of my eye. Okay, obviously these rays are going in 360 degrees, but we're just focusing on the ones that are going to hit the eye. Okay, this ray leaves, hit the bottom, and hits the bottom of my eye. Because of the divergence in those angles, though, my eye can see the top part, see the bottom, and actually recognize that there is an angle between the two of those, such that if I traced that angle backwards, it would be right over here. Okay, is there obviously an actual object there? No, this is created by our brain due to the fact that our brain does not think that light reflects, does not think that light refracts. It assumes light travels in a straight line. Make sense? Cool beans. All right, so let's talk flat mirrors here real quick. It's going to be a real quick conversation, though. Okay. Now, we're going to draw a lot of what are known as ray diagrams. This is kind of the force diagram of optics. Okay, and there's a few rules that you can follow. Sometimes with flat mirrors, you kind of got to do your own thing and kind of try to figure out just geometrically what's going to happen. You'll see that on some of the problems. But what you look for a lot of the times is this. Okay, I look for, say, this ray right here. What would this ray do if it went straight into the subject? It would come right back at the exact same angle it came from. Yes? Meaning my eye would assume it came along this line right over here. Okay? Then, because of the law of refraction, here's the object going down, bouncing back over here. Okay? Why am I choosing this exact spot? Well, because I could probably very easily measure this particular angle simply by measuring the height of the image as well as knowing DO, how far the object is away, which should be relatively easy to measure with a meter stick, a ruler, whatever, that type of thing. Okay? And if I followed that back, what I would get is this right here. Now, what you should notice very importantly is since this angle, these two angles are the same because of those two angles are the same because of this, yeah, not geometry, last chapter, law of reflection. Okay, these two angles are the same because of alternate interior, right? Alternate interior in that particular case, aka you have two straight line objects like that, you know those are the same. By the way that you could prove that those are the same really quickly here is both laws of supplementary angles. That being, hey, what is theta plus phi going to equal? That's going to equal 180. And what are these two going to equal since it's also a straight line? Also 180. So you could easily prove that those two are in fact the exact same measurement geometrically. All right. Now, what you can then do is you see these triangles. It says the triangle PQR, so it's referring to this triangle right here. Yes? And P prime, we usually use primes so that we can do them very quickly to signify over on the image side. But these are identical triangles. Yes? This angle is the same as this angle, is the same as this angle, is the same as that angle. Right? So they are all similar to one another. And you can see they have the exact same side over here. Right? So if they have the same side and one of the same sides and the exact same angle, are all of the sides going to have to be identical to one another? Yes. This is the proof that these two distances have to be the same, or what we would say now, what we are going to say now is that obviously DO is equal to the absolute value of DI. We'll talk about why there's an absolute value on that a little bit later. And that H is equal to HI. H being the height of the actual object, okay? And HI being the height of the image. Okay, now the reason why those heights matter is this next part of the conversation. An eraser. Let's get rid of this real quick.
Is this an always thing or just in this scenario?
What do you mean?
Like with all flat mirrors?
With all flat mirrors, yes.
Okay.
Yeah, this would be.
Not the case with the curved mirrors. Yeah.
We'll get to the yes. No, it's definitely not the case with 100 mirrors. Okay. Notice what it says over there. Magnification is by definition equal to the height, image height, over the object height. Now this is one of those equations that I always like to be like, please don't think too complicated about this. I imagine most of you intrinsically know what magnification means. Okay? Like if I told you magnification is 2, what does that mean?
Stuff looks
Twice as big. So we're just measuring one dimension of that. But specifically, that would just mean the height of the image is twice as big as the height of the actual object. So, since these two are the same, the magnification of a flat mirror is going to be 1. And what does that mean whenever you look in a flat mirror?
It looks the same size.
You should see yourself in the mirror the exact same height as what you normally do, and that is regularly our assumption. Yes? All right, moving on. Now, so flat mirrors. The image is as far behind the mirror as the object is in front, and the image is unmagnified. Let's talk about virtual in just a second. Unmagnified simply just means 1 and 1. You get a magnification of 1. Okay. Your other options on magnification are going to be enhanced or reduced, which you can imagine enhanced is greater than 1, reduced is less than 1, but we'll worry about that later. Let's talk about virtual for a second. Now, I'm going to tell you the truth. I'll tell you the answer to this because I think it's important here. Let's make sure we have headphones out if you don't mind. Okay, it won't make sense until you get the opposite of a virtual image, which is known as a real image. But a virtual image is this. The rays combine where there are not actual rays. There is no actual ray there. This would take place in your brain. Okay, meaning if this is the mirror, this screen is the mirror, I stood here, I should see myself on the other side. Yes? If I held up a piece of paper where the image should be, will anything appear on the paper? No. Thus, that image is created in my brain, not actually there in real life. Yes? We will actually see, like I said, it's kind of weird to think because that's what you're used to. That's what you're very used to. But there are going to be images that are real, in which case, yes, that's where we see the image, and there's something actually there. You'll get kind of a quick lab today, per se, where you get this the same type of effect. All right, let's get that in just a second. So Image is unmagnified, 1:1. Virtual, there's nothing actually there. And upright, you get it, basically the image is the exact same direction as the way we usually see it. All right, this one's a little bit tricky. Don't answer too quick. Stop being a butt. All right, what you got? Where does observer 2 see the image? Any thoughts? What's your gut feel? Your gut feels what?
E or F.
You got D?
E.
E, I'm sorry, you're thinking E? Okay. So the idea, make sure you're thinking about this part carefully. So the idea is, if you looked all the way over here at E, would you see the rock?
Yeah.
And that's not it. What's up? The answer is weirdly C. Now what you have to do, in order to understand this, is think about the law of reflection, right? What's going to happen to person 2 in order to be able to see it? Well, rays, here's person 1, right? That ray bounced off and person 1 saw it. Is that ray ever going to hit person 2? Is that ray right there, the one that goes that way, ever going to come over and hit person 2? So what's the one that's going to hit person 2? If I shoot this ray, will person 2 see that ray? Nope, definitely too far. So let's split the difference here. Let's actually literally split the difference, okay? And go, this person, actually no, I did it too far. Not far enough, arguably. I split it in half, but I shouldn't have. Come on, come on, thank you. Okay, it would be that is the ray that would actually get the same angle on both sides. Yes? And if you trace this particular guy backwards, it hits right there at C. That's definitely one that when I did it the first time, I think I said, I had the right idea, I think. I said B when I said it, which is definitely the right idea, but in order to see it, here's how you could kind of think of this. In order to, oh, hello, what are you doing here? In order to see it at B, the ray would have to come from here. Do you see that? Okay. So notice one thing that I'm doing as I'm kind of figuring out this problem. The dotted line that's over on the other side is the virtual, that idea that my brain assumes it goes in a straight line. So it has, there's the image, dot, 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 dot. Then I go with an actual ray, because it has to be an actual ray that hits you in the eye, right? Will a virtual ray hitting you in the eye do anything? Well, let me ask you a question. If I look into this mirror and see me, and you look from over here where the virtual is, are you going to see me in the mirror? No, obviously not. Okay, moving on. So flat mirrors actually are, this is an old school style thing, but this goes to the idea of using both reflection and rarefaction at the same time. You ever see on, most of you probably have this, and I would imagine that most of you don't use this. There is this physics principle that is actually used by rear view mirrors to kind of give you like a nighttime vision that most people don't do. If you look at your rear view mirror, assuming it's not like a modern one that actually can like change its how much it reflects, okay, which you might not be, especially if you have an old school. There is a thing on the bottom that you can flick and it will change the angle. You know what I'm talking about? Yeah. If you don't, check your rear view mirror tonight and look for it, okay? That is actually so that you can, at nighttime, not get blinded by the people behind you, but still see the people behind you. Because here's what happens normally. daytime setting, okay? If light comes into this guy right here, okay, there's two things that happen. One, some of it gets refracted and some of it gets reflected. I imagine you probably know this. If you had to guess, does more of it get refracted or does more of it get reflected? No. More of it gets refracted because, watch here, it gets refracted, it goes in, the mirror is over here, it bounces back and then refracts back into your eye. Now, the cool thing about this particular principle is while it is complicated, it doesn't take you complication to set up. Why does it not take complication for you to set up? How do you know it's in the right angle? What simple thing does everybody do with a rear view mirror to check if it's at the right angle? They know it's at the right angle when they can see the people behind them. Yeah, when they can see behind them. And then, so good, you just can look at it now. Think about your rear view mirror. Is your rear view mirror perfectly lined up? So it's like, no, because then you wouldn't actually see what's behind you because you'd hit and you'd actually see, what's below you in that case. All right, going back. So watch here, the incident light. Imagine this is the ray from the car immediately behind you. Some of it reflects, right? Now, do you see the reflection? No, you're up here. So then some of it refracts, hits the back, hits here, and what do you see? You see the car behind you. Yes? Okay, no big deal. Most people never switch it past it. Most people are using the daytime setting all the time. But the nice thing about the nighttime setting on your rear view mirror, that this is lost on most people, so I don't know if most car companies even make them anymore. I'm really curious how many of you actually have one. It's just a little physical switch, and if you do it, if you hit it, it'll just take your rear view mirror and angle it a little bit upwards, okay? So instead of here, it'll go here, and here's what ends up happening. Notice, the angle going in is the exact same angle of incident light before, but the amount that gets refracted now comes up here. Are you gonna see it? No, you're only gonna see the amount that is reflected. Why is that nice for a nighttime setting? When there's huge amount of headlights pouring through the back of your thing and hitting you in the eyes, so you don't have to use glasses at night or anything like that. You flip that up and a much lower percentage of that light comes through, so you can still see everybody behind you, but you don't get blasted with the full strength of their headlight,
For the Ford F-150, it's brights on free.
Yeah.
Yes.
110%. Yeah. Questions, comments, concerns here? How many of you knew that was a thing ahead of time?
I learned about it like a month or two ago.
Is that right?
Then I started using it every time there's like a bright LED behind me.
Super nice, right?
Yeah.
Like I remember, quite frankly, I think I learned about this, I'm really embarrassed to say, when I was teaching Physics 2 for the first time about 5 years ago, and definitely use it the same anymore. Now, like I said, we've also got like a van that has these these fancy ones, and the fancy ones, a lot of times the digital display will actually self-reduce now. Like they don't actually use these principles. They just kind of basically give a tint to it so that you're not getting hit with the full strength, but there it is. So check that out on your way home. Check your car or your parents' car or whatever, and here we go. All right, let's talk about spherical mirrors. For starters, every mirror that is spherical, by definition, is basically the outside part of a sphere, meaning it has a center. I'd like them to go down. I put them over there hoping that somebody would take care of them, if somebody would take care of them today. So here we go, flat mirror, blah, blah, blah. You don't need to see this. You look at it every single morning. Okay? So this is what we are talking about, a curved mirror. Okay? Now the interesting thing about the curved mirror is it depends on where you're in the room based on what you see. Kian, what do you do? Can you see yourself in here right now?
Yeah.
Okay? What do you see?
I'm upside down.
You're upside down. Jordan, you're
Upside down.
upside down. Okay? Cass, you're right side up and very large.
A big circle. Can't see anything. Yep. Oh, right side up.
Right side up and very large, yes?
Mm-hmm.
Okay. Now, all of you in the room are not going to be able to see cast that particular way based on the fact that you guys are at a different distance. And actually, I was on a cast on you just hit. Okay. Actually, let's do this. Can you see cast right now, Keen?
I can.
No.
You can?
I see Gavin and Terry.
Oh, I see my head upside down. That's a lovely angle. Oh, that.
Okay. Can you see cast right now? What is she? Sorry. Tell me when you can.
A black sweatshirt.
Wrong way.
Opposite. You're going down now.
So it's hard to say. Are you here? It's hard for me to see without this. I'm guessing
I see.
because
green now.
you would think oh, this is obvious for Spainhour. He should just angle it up so that you can see up. Because if it's backwards for him, I don't want to do that. So what do you see cast now?
I see halfway between Cass and Kean.
Okay.
Turning.
Good there. See her face? Upside down, right side up.
Upside down.
Upside down. Cast once again. Upside down, right side up.
It's just right side up.
Right side up. And
It's
can you
like
see her
just
still?
black.
I see very close to her neck.
Yes, no?
I see a sweatshirt. Turn a little bit sideways. Other way. Yeah.
Right side up, upside down.
Oh, he's upside down. That's fine.
So, depending on it's the distance to the object and also like the observer to a certain degree kind of changes what you're looking at here. Now, first thing to understand is this. What is the center of curvature? It's the center of a circle. Okay? If you imagine I drew this all the way a perfect circle, right? Then this is, yes?
You sound like my car.
Then this is simply the radius of a circle, yes? So, does this, you should be able to do this probably relatively easily, which has a larger radius? This guy, don't even worry about what you're looking at. This guy or this guy?
That
Big guy.
second guy.
Big head.
They're both big. Which one is the bigger radius?
That
bigger one.
It's not this one.
What?
What?
Why is this one the bigger radius?
I don't know.
I don't know.
Then think about it.
That's not my strong suit.
Why are you here then?
To work on it.
It's a
So let's work on it.
smaller part of the story.
Irritation here is not that you don't know, it's that you guys guessed in 5 seconds and not irritated at me when I wanted you to think about it longer.
Why don't I know it?
I thought about it and then my thinking was wrong because you said it was wrong.
We just
You
did.
thought about it for 5 seconds.
No, I was like, I think about it.
Okay,
I was taught by
so-
understanding.
Okay, it's wrong.
But it-
Fix it.
I can't think.
Why? I'm telling you the answer. This has the larger radius than this one. Why? Let's try a different game.
The angle.
Somewhat. Let's try this again.
It's a smaller section of the
Sorry, Morgan, for the in-person demonstration that you're not seeing.
Oh, that must have been
Oh, I
irritating.
forgot. Morgan's being
Yeah.
not
Hi, boys.
present.
What's the largest radius?
The second one.
What?
Is the first one meant to be a straight line?
Mm-hmm.
Okay.
Is it the one that's curved the most?
Is it?
Is it the middle?
One that's curved the least.
What'd you say?
Let me draw several circles here.
The middle.
Okay.
That's Billy Bob. And that's
Okay,
Betty
which one is the largest radius?
The third.
Betty.
Obviously.
One.
The biggest one.
Which one has the largest radius and how do you know?
The third one, because it's
Still the third one because,
I don't get it. 'Cause that
It's
was
got
bigger.
the.
the angle, the
It's got
curvature
the
is
least.
less.
yeah, it's got this, so actually, weirdly, if we play this out and come back here,
It's the straight line.
a straight line is a curve with a radius of
Infinity.
infinity,
Oh, that's weird.
which actually will play with our straight mirrors a little bit later on. Okay, so once again, y is, let's make sure we're up here, are we good with the fact of why, let's comparing these two, why this one has a larger radius?
Yeah.
Cool. What do you mean? Okay, let's go back. Are you good with why this one has a larger radius?
Is it 'cause it's closer to being straighter?
I mean, sure, but it's basically just, when are you going to go through the most angle? What, bigger radius or smaller radius? I choose an amount of distance, a very small amount of distance.
1 centimeter.
Assuming they're all about the same distance, how can I easily see that the one on the right has the larger radius? It's gone through less of the curve, right? The same amount of distance on a circle that is larger will go through less of a curve, right? Or to a certain degree, sure, the one with the larger radius is straighter, right? If you want to think about it like this. Imagine that you took that curve, imagine that you took that circle and you kept going, right? Would it make a tighter circle or a bigger circle? Which one of the two of these will make the tighter circle?
The larger one.
This guy. I don't know why I keep saying larger. They're roughly, they're about the same. They're not that much different. I mean, this one's a little bit thicker, I'll give you that. But also be careful with larger in terms of physics, because larger volume, larger mass, larger
volume, actually.
Okay. I say mass, I'm cool with that, but it's actually not that far off. All right, so the larger radius is the one that is less curved. Yes? Okay? Meaning, if I wanted to continue this guy and make a circle versus make this guy into a circle, you could see that this one will have, I didn't do a great job artistically, but this one definitely has a larger radius. What's that? Doesn't seem like the focus that we should be on right now. Do you feel comfortable now with the, okay, moving on. So, the point of curvature is the center of that circle, right? So if I were to take this guy and continue around, I didn't do, again, a great job artistically there, but you can see ideally that the C is meant to be the center of that circle. Cool? Cool. Let's move on. So, if rays diverge at small angles, they will always reflect through point I. All right, so in other words, I don't know why they talk about that. I don't like that. I'll come back to this. Okay. Images formed by spherical mirrors. Rays intersect at different points on the principal axis, depending on exactly where it hits, if you're leaving the point of curvature, which is why we have to kind of compare it to different spots, and we're going to need ray diagrams, but we'll talk more about that in a second. So here is a beautiful ray diagram that will help us in this particular case. Okay, now watch carefully, watch really carefully so we can understand this principle well. Okay, does this make sense to you, this first blue ray right here?
Yes.
Okay, next. This one's a little bit harder, but hopefully you should get. If I go through the point of curvature, why should it reflect back always and go just opposite direction?
Exact straight flat line with whatever point is.
What is the point of curvature?
Center of the circle.
Okay. So if I draw a ray through the center of the circle, what is this line over here? The radius. And how does the radius always hit the outside part of the circle? At what angle?
Usually outside part.
At what angle does the radius hit the outside part of the circle right here? 90 degrees. And if you put a ray in at 90 degrees to the surface, in what direction is it coming back out? 90 degrees. AKA, here's a flat surface. Okay? If I start here and I hit there, well then law of reflection says those two angles are going to be the same. Yes? But if I go here and hit at 90 degrees, that angle is 90. So what's the return angle going to be? In other words, it's going to go right back from whence it came. So, coming back here, that's why you see these two arrows pointing in, basically it's the same arrow, sort of, but it's saying it's pointing in this direction because it goes down here and hits the mirror, but since it hits at 90 degrees, what does it do? It comes back the opposite direction. Yes? Now, watch carefully to this next part. Do rays converge at a particular spot then? Do these two rays, the blue one and the red one, converge at a particular spot?
Visibly, yeah.
Yes. So, your image is upside down, reduced. And is it real or virtual? Start with the first part. You see why it's upside down, yes? The original was going this way. The one is upside down. Cass saw herself upside down. Yes? Now the rest of you didn't, which we'll talk about why. And just, I'm sorry, Cass saw herself right side up. The rest of you saw her upside down. We'll get to that in a second. Okay? So, excuse me, saw her upside down. Why is it? Why did I say reduced? According to the picture here. Look at the size of H and the size of H prime. Are we seeing both the image and the object at the exact same size? No. Unlike a flat mirror, which was 1 to 1, in this case, the object appears to be upside down and smaller than it actually is. Yes? So, see the way you look in a flat mirror. Okay? You see it? Let me know when you see it. You see it?
See what?
See yourself. Just roughly how big you are right now. Can you see yourself in the mirror?
With a very low forehead.
I don't know which way to go. Can you see you right now? Yes or no?
Like my forehead, like a very long forehead. Yes, technically, I guess.
It's got a little stretch. It's not the best flat mirror.
It's not, but it's pretty close. You see you. Any of you tell me to move.
I saw
I
Lucas.
see me.
You see you. Good.
We saw white Lucas.
You see
Yes.
you.
Yes.
Good. You. I can move it. Just let me know which way I gotta push it.
White Lucas.
Oh no.
Yeah. I have no clue where
I
you're even
think
pointing
that
right now.
could
I'm
get
not
even
gonna lie.
wider.
I'll try, and then you tell me.
Yeah. I was stretched. There you go. Move back.
Cool.
Up a bit. Over.
It's like a football sphere.
It shouldn't be that bad. What are you talking about, stretched? This is about right.
Wait, hold it back though. Hold it far away.
What's that?
You gotta
Hold
see
it far
white
away
straight
from
hour.
here.
White hour.
Well, now it's long hour because.
I mean, sure, a little bit. It's not that bad though.
That's what I, no,
Okay,
it
for the
was
most
bad
part,
me.
for the most part, it's about what you should see. You guys are. Now,
If I see that in the
Look
mirror.
again. Look again. Tell me when you can see you.
I see his toes.
Okay. Not him. When you see you, I gotta move it. You guys are being buttheads. This is irritating.
I see me.
Okay. You see you.
Yeah.
Are you upside down?
Yes.
Are you smaller than what you saw a moment ago?
Yeah.
Yes. Same? Okay. Same? Hold on, Cass. Same?
Yeah.
Okay. The fact that you see yourself upside down is why it's inverted. The fact that you see yourself smaller than you should, okay, it means it's reduced. Now let's talk about real. Why? Any ideas why this image is real as opposed to being virtual?
Both of the rays converging at that point are real.
If you put a piece of paper right here, you will in fact see a small image of you upside down at that particular location. Okay. Now, so because of that, let's do a little bit of trig here. Well, actually, no. Basic magnification is by definition height of the image over the actual height. Now notice, I'll do the math on this real quick. I think that are they going to do the math or not? Yeah, they are. Okay, so I'll do that in just a second. But that says this is these are equations you definitely want to have down. And I would put them separate. I would put that magnification is equal to that. That's the first one that we've dealt with here. And this, that magnification is equal to negative di over do. This equation, both of these equations are on your AP equation sheet. Now, let's talk a little bit about why and what the heck's up with that negative. All right. Basically, your general rules of lenses and mirrors are as follows. Where it would normally create a virtual image is given the designation of negative, okay, negative distance. If it would usually create a real image in that spot, it is considered positive, positive distance. So, on the left side would always be positive. So DO is always going to be positive. Now, what you see here is, where is it possible to get a real image? In the case of a mirror, that's simple. It's in front of the mirror, right? You're going to reflect the rays. They're going to hit at this location. You see that those are actual rays because those are solid lines, not dotted lines. So a real image in front. So what I do is I say that this, which is DI, is positive in that particular case. Yes? Now, notice a few things that make sense here before we get into the math, and that is, which is bigger, DI or DO? DO, just based on some pretty basic geometry here. So that means that if DO is bigger, okay, magnification-wise, that means that this has to be reduced. Yes? Has to be smaller than what we normally see. Yes? What's the negative mean? Well, if both of these values are positive, that means my magnification is negative. Guess what negative magnification means?
Smaller.
No. Smaller was the fact that this is less than 1.
Correct.
That's what makes it flipped. That's what makes it inverted on the opposite side. So that means, can you get two positive numbers? Can you get a real image and still have and ever have a non-inverted number? No, the only way you are going to get a positive magnification is if one of these two is negative, aka it is a virtual image, which we'll talk more about later. But right now, let's just do the math on this guy real quick, the same way as we did the last one. Okay. So similar to this last one, by the last one I'm referring to this guy, we're going to do some basic trig here to show what these equations have to be, basic geometry. This basic geometry showed that these two equations were similar. So how can we do that over here? Well, we're going to look at the triangles. I'll highlight the triangles for you now. We're going to look at the triangles, right? Oops. Forgot that was an eraser still. Come on. Right here. This first triangle. Okay? And you know two sides of that triangle. What are they? H is the first one. C is not a distance. C is the point of curvature. What is the other part of that triangle that you say?
Hypotenuse, I guess.
You don't know the hypotenuse.
Angle?
You do know the base. What is the base of that triangle?
OV.
What's that?
OV.
No. I mean, sure, you know it's over. That's not a number that makes sense to us. Oh, no, diameter, you don't necessarily know. Diameter is probably right here, but that doesn't matter to us. You know that that is DO.
Oh.
Oh, I didn't see those down there.
Sure, you don't have to see them. You should also just recognize that's the distance from the object to the mirror, DO. Okay? Now, what are we going to do? Well, we want a similar triangle here. Okay? So, let's use this triangle actually. Well, they're using a different triangle than what I said. So let's try this. As a matter of fact, I was wrong on the triangle they're using. So let's use a different triangle. Let's use this triangle right here. Okay? And then we're going to use this triangle right here. Why? Well, what do you notice about the angle alpha in this particular case?
They're the same.
They have to be exactly the same. So, what is the tangent of alpha? The tangent of alpha is going to be the opposite, which is just h. Yes? And the adjacent is this side right here. Now, if the entire side is DO, okay, then I just need to subtract this piece off over here, which is just going to be what distance? The distance from the point of curvature to the mirror is the radius. So that's why you're looking at DO minus R in this particular case. And now we look at the other triangle. What's the other triangle? The other triangle is going to be this guy right here. What's the opposite of that? What is this called? The height of the image. This is the height of the object. This is the height of the image because you can recognize by the prime. And using that same line of logic, what is this? Well, you told me this a second ago. What is C to there? Radius, right? And what is this distance right over here? What is this distance right over here? What's that? DI. So, come on. That's where you get this right here. Now, how are these ratios going to compare? Oh, why is there a negative on this one? So height is negative, right? When height is below, height is negative. So to get the angle I have, that's technically a negative h prime. They just move the negative out in front. So what can I now do? I can set these two ratios to one another. And I'm not going to do that right now. I'm not going to go through that math, but I'd like you to. Okay? I'm going to check your work tomorrow, first thing when you come in. I'd like you, if you haven't yet already getting this down, I want you to set this ratio equal to the next ratio and try to prove the next thing that we're going to say. And that is that the magnification of h prime over h is equal to, once again, this right here. Actually, it should be a negative on that. So this is the proof of this guy right up here. So I would like you to take this ratio and this ratio and show that h prime over h is in fact equal to this right here. Now, you are welcome to use this work that they're attempting to show right here. My experience with doing that is it's really hard to explain this individual piece right in here. So I would highly suggest you do the work yourself. We'll talk about that first thing tomorrow, though. Okay. So let's talk about something else that is kind of important here. So here's what we have right now. We have magnification is h prime over h and is also equal to negative di over do. By the way, if you ever forget the order of is it I or object on top, think of your basic idea of magnification, right? Your basic idea of magnification is the object is not going to change. It's not going to change what's the object at all. You're going to change the image. So the question is the image getting bigger or smaller, which is why it's the thing on top being compared on the bottom. All right, now, what if the object di was out at infinity? I thought there was supposed to be another thing here. Oh, yeah, there is. Come. Well, I thought it was the next last page. Oh, no. Okay, my apologies. There are two things you're supposed to do with this ratio. The first is to show that these two are equal to that. The second is to show that this is the case. That is 1 over di plus 1 over do is equal to 2 over r. Let me write that out. Not on this page right now. We'll discard. Now, let's say the object is out at infinity. Okay? What does that mean? Well, this new thing I'm going to show you is a new term, but I know you have heard it before. So it's somewhat hard to explain, but it's what's known as the focus. And the idea is if you have rays coming in perfectly parallel, okay, by definition, every ray that comes in parallel to a spherical mirror will bounce back, and every single one will always hit the focus. Now the thing is, the rays have to be parallel. You actually saw earlier on a slide, this one, when the rays don't come in perfectly parallel, like this one and this one and this one and this one, you'll notice they hit at different spots. Absolutely they can hit all over the place. But what we're saying is if the rays come in perfectly parallel, all of these will hit the point known as the focus. And if you've heard absolutely anything about cameras and that type of thing, or photography, or that's the same thing. Video cameras, you definitely know that the focus is a particular thing that I talk about all the time to get something into focus. Now, you usually don't have to worry about this because your camera naturally does this thing, but we're going to talk about the actual physics principles that your camera relies on, that your phone relies on, in order to actually make this thing happen. So, back here it is. Where would the object have to be in order to create rays that are perfectly parallel?
Very, very far away.
Or if we wanted to kind of get ridiculous with it, we could arguably say infinity. Now, if that's the case, if you look at this equation that we had on the last page, that number would become infinity. So what happens to the whole first term? Essentially, it's 0 in terms of calculus, yes? Which now means, by definition, that 1 over the image, the 1 over the image always has to equal 2 over r, right? If basically all I said was just, hey, if that's 0, then 1 over di has to equal 2 over r. Yes, if that equation is true, and I don't like that, so let's go ahead and flip both sides. That means the focus, if the rays come in from parallel, they will always go to the focus. And what this says is that the focus is always at what? Half the radius. Always. Now, which one's probably going to be easier to spot? The focus? Well, actually, that's debatable. But could you probably measure the radius of a circle? Yeah. So how do you then find the focus? Cut that in half. Now, the other nice thing about the focus is this. I've tried not to do this so far, but I'm going to pass this around now. Okay. Your eye requires there to be a deviation of angle. Let's reverse this process. Rather than the object being out here and going entirely through the focus, what if the object is sitting at the focus? Well, if the object is sitting at the focus, we just reverse this. Instead of all of the rays coming parallel, right, and converging here, now we start here, all the rays go out, hit the mirror, and what are they going to do? They're going to come out parallel. Is your brain then going to be able to find a common point where those rays meet? If they're coming out parallel, if we reverse this and go the opposite way with it, right, we look over here. Come on. Come over here. Is it going to be able to ever converge? So can your brain tell you a location? Which is why, if you do this, you look at yourself, the moment you hit the focus, try to make sure, you can't see jack squat anymore. It's fuzzy, it's weird, it's all over the place, because your brain's like, what the heck? I can't draw any sort of combination of things, and your brain short circuits. And then, outside the focus, that's when it will flip. And we'll talk about why it flips in a minute. Actually, this is not the one you want, because this has a very large radius of curvature. since this one over here has a smaller radius of curvature, it should also have a smaller focus. So what I want you to do is I want you to take this, okay, stand with it next to you. Oh man, that's a really good image of me. I am definitely magnified. This is why you use concave mirrors, by the way, for the purposes of makeup. So you can make yourself seem much bigger, and so you can kind of really focus on the details of your face, blah, 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 blah. Good. So what you do is you take it, pull it away. When you're at the focus, it's going to look wonky. Then when you get beyond the focus, you should still be able to see yourself, but you will 100% be upside down and a little bit reduced. Try it.
Oh, that is lovely.
I'm going to actually tell you what I'm going to do. Let's put this down for a second. I'm going to have you do this as one demo in a minute, okay? And then I'm going to actually have you guys do two other things here at the end. I want to try to finish one other thing on the notes, and then I got like two demos I'm going to walk you through, the latter of which is just going to take you to the end of class. You're going to work with the group to try to find something else. Only other thing I want to show here is this. All right, so this equation appeared on the last page, one of which I want you to prove for tomorrow, okay? This guy right here, right? Well, if focus is r over 2, then 2 over r is just 1 over focus, right? AKA what I just said there was this. If f is 2 over r, then 2 over r is 1 over focus. So that equation I shared with you a second ago, this is ultimately what you're going to want to use. Okay? So your three basic equations as it stands right now for mirrors are as follows. Magnification is equal to h prime over h. That's by definition. It is also equal, with spherical mirrors, to negative di over do. In addition to that, 1 over di plus 1 over do is equal to 1 over focus. Now that feels like a lot of variables, but if you're really closely attentive to this, what you'll notice something is this. The only thing you actually have to control in order to get a particular image is this number right here. Focus. Because if you control the focus, the object is going to be some distance away, right? But once you have a focus for a particular distance, is a distance of that image always going to be in the same location? If these two numbers are set, is that number set? Let's say this differently. If I want you to change the focus, what do you have to do? This mirror has a particular focus, yes? What is it? Half the radius, okay? Does the... They're too freaking big to walk away. Does this have the same focus? Why or why not? It does not, because
Radius is
smaller radius is bigger. And this is the bigger radius, right? It's less of the circle, so bigger radius. So the focus is bigger, correct. Bigger focus. This is why this was actually harder to do with this particular demo. I do have short arms, so if you have longer arms than me, you can probably pull it off with this one. But almost everybody is going to be capable of doing this one over here because smaller radius, smaller focus, easier to demo with that particular thing. Okay, so is the object definitely going to be, if you're dealing with this, is the object going to be some distance from the mirror? Yes. At that distance, how do you change the focus again? Different mirror. There it is. Different mirror. Or if you could somehow change the shape of the mirror, like our eyeball, hey, our eyeball is capable of changing this, isn't it? Watch, I'll show you. Okay? As a matter of fact, you can see in someone's eye, it's very, very careful, but you got to kind of look from the side. But if you look from the side of somebody's eyeball, okay, really carefully, have them look at something very close, and then immediately look far away. And what you'll actually see is like the shape of their eye changes. Okay? If I want to look further away, I need my focus to probably be a little bit further out. So what my eyeball does, I'm going to be kind of exaggerating here. Here's the eyeball when I'm looking closer. I want to increase my focus so my muscles in my eye stretch that lens out so that now it has a larger point of curvature, a larger focus. Actually, I might be backwards. That's not important. But that's essentially what's happening. You're changing your muscles so you can do this. But can I change the shape of that particular mirror on the spot? No. If I'm taking a picture with a camera, can I change the lens on the spot? No. So what do you do if you want to change? Change the lens. To change focus, you have to change the actual material itself, right? What do you do if you want to change DO? Move away. You just position it the distance away. Once these two are set, is this one set? Yes. And if these two are set, is magnification set?
Yes.
This is why I can be very confident based on where you are in the room. What am I changing when I'm looking, by the way, if I'm having you look at you, okay? What am I changing when I have, say, I pointed at Cass versus pointed at Jordan? Why does Jordan see himself as upside down and Cass sees herself very big and in front of her? Which one? Changing DO. Because what's the object in this particular case? People. Yes, the people themselves. Now it's a little bit interesting when you are both the observer and the object. Okay? So if it helps, let's pick an object that is not also the observer. Okay? Cass, what do you can you see Yoda right now?
He's upright.
He's upright and larger? Okay. Actually, let's just do this. Now, hold on. Here we go. Okay. Yoda.
Tilt down. Yes, I see him.
He is what?
He's upright.
He's upright and
very big.
larger. Notice in both of their cases, it doesn't matter where the observer is, right? What matters was the distance to the object. I attempted in both cases to have distance to the object be the same, right? So what was changing between Cass and Jordan is not where they were observing, but what they were observing, right? Technically, if I have Jordan attempt to look at Cass, can you see Cass?
Can't set it this way.
Can you move your head?
Yes.
Okay.
She's very large.
Sorry,
very
Cass, you were
upside
just
down.
in front. I'm sorry. I really should have asked. It's rude of me to just keep doing this. Here, let's do me. I'm sorry. I apologize. Okay. And actually, this would be easier because I can kind of like get a sense of whether or not you can see me or not. Kian,
Oh, that's a wonderful image.
Kian, can you see me? Actually, yeah, 4 of you can see me. Am I big?
Can I take
Yes.
a photo?
No, you can't. I'm so not. Okay.
It
Okay.
looks like Tom.
So I am big and I am magnified for all of you. Yes. Same thing again. Less of you are gonna be able to see me. Hold on, I gotta find me.
Oh yeah, oh that's good.
Oh, yeah.
Now watch. Watch carefully.
Straight up the nose.
And they're,
But you're still upside down.
I was already. I shouldn't have been upside down over here.
yeah,
Yeah, you're
still
up.
upside down.
I'm upside down for you right now.
yeah.
No,
Yeah.
no,
You're a
not.
slight
I'm
lady.
kind of between.
You're an angle just below.
I guess that does matter on where you see it in here. All right, fair enough.
Yeah.
All right. The whole point of this is you can control focus of the mirror and you can control like one of these things.
We're having fun, Morgan.
These are the 2 things you can control.
You're
Once you have these 2 things set, DI is in a particular spot, and magnification, therefore, is a certain amount. Okay, so it feels like a lot of variables up here, when ultimately, because of ratios, you really actually can only control a couple of things. Okay, so here's what we're going to do. I got these mirrors out for you to play with. Yes. The other thing that I want to show you is a visual representation of this right here of focus. Okay, so I'll do that here in just a second. I'll grab some stuff from the back and do that. And then the last demo, after you look at those 2, and it probably shouldn't take long, is simply this. If you look at this particular setup with a curvature concave mirror, so this is concave, we haven't got to convex yet. Okay, just a heads up, this guy is the convex one. It's just like what side the mirror is on. It's on the inside part of the circle. Simple put, in case you've never heard this, the way to remember cave, you can walk into a cave. So that's like when you're dealing with concave. This is not a concave mirror. This one is the concave mirror over here. Convex, I don't have a good one for that, but this is your eyeball essentially. The outside part of the circle would be convex. We're only ranking on concave. Okay. Once you've done the first two demos, here's the last thing. I'm going to draw a picture. Okay. I'm going to draw a picture and I'm going to put it in the window. It's going to be a dumb picture. It's not that important what the picture is of. It's mostly so that you can use that as the object. Okay. Then what I'm going to want you to do is take a concave mirror. I got two of them up here, and I'll grab another one from the back, and you are going to try to find the real image. Meaning, if it's real, you should be able to put a piece of paper at this location where they meet, and you should see an image appear on that piece of paper. So you take a white piece, you could use like a notebook. Just take a notebook, position it around, and try to find the real image being reflected on the opposite side. So again, your demos are, take a concave, see that flip, find the focus. 2, I'll get the focus demonstration up here in just a second. And 3, the one that'll probably take you the bulk of the time and into tomorrow, please make sure you do that math also for tomorrow, is going to be find the real image. I'll put an image up on the window over here, and you guys are going to try to move around the room and try to position this mirror and the piece of paper so that you can find it. Make sense? Work in your groups, please. Morgan, that's really it for me, so I'm calling it early.
Bye, Morgan.
Bye.